Good afternoon, everyone. Today I'm presenting our work with the title Capturing Ambiguity in Artifacts to Support Requirements Engineering for Self-Adaptive Systems. This work is a work in collaboration with Juan Munoz, myself, Lorena Costañada, Mahdi Manish, Robert Heinrich, Matthias Becker, and Nina Taheri. And this work was a result of the Dagstuhl seminar on software engineering for self-adaptive systems for the junior researchers. And at that time, in 2014, we have all been PhD students. I would like to outline my talk. I would like to start with the motivation, then presenting our approach on artifact-centric RE activities, and then conclude and present future work. Let's start with a motivation example, and I would like to take the example from the keynote today on autonomous vehicles and the requirements refinement. So, autonomous vehicles originally started with just general vehicles, and then first it started with adding more and more sensors to be able to capture the context. And after we had many sensors, then we incrementally added more features. So the features then use the sensors to understand certain situations at runtime to support the driver in certain functionality. And then over time, more and more autonomous features were added, which were partly determined at runtime. For example, continuous experimentation can be used to determine whether one feature is better than the other one, or the same for context situations, whether certain context situations are applicable or not. So let's take the example of active safety systems. Active safety systems are software systems that are integrated into vehicles, and they help the driver to prevent accidents or at least mitigate the implications of accidents. Originally, data of accidents is analyzed, and then this analysis can help in determine which functionality is needed to prevent these accidents, and also to determine the context and certain situations in which accidents occur. And also from the accidental data, test cases can be derived. Those test cases then focus on specific types of situations that need to be tested, and also whether other vehicles or objects need to be involved in the testing. As for example, on the picture we see a dummy of a pedestrian. It's not a real pedestrian, it's a pedestrian that is used on a proving ground, and it is meant to represent a real pedestrian to test the triggering of certain features in the vehicle, in this case in the truck. So the pedestrian would walk and the truck should recognize the pedestrian and then brake. And currently Volvo has a Drive Me project which will be delivered next year and will have autonomous vehicles driving around Gothenburg on Gothenburg streets. And for that, Volvo is preparing by already analyzing the streets and trying to understand the situations that will occur on the streets. Then the idea is when the vehicles are delivered, they will collect runtime data and analyze these specific contexts and situations. Now they start with testing on proving ground, as for example at Asta Zero. And then they will use the vehicles in real-life context. And for example, again, coming back to continuous experimentation could be used to determine the best possible option for a certain implementation. So here we see the application of runtime analysis and trying to understand how can we refine or maybe improve functionality, or how can we identify context situations in a better way when really trying it out in real-life context at runtime. So we move from design time to runtime, and this inspired us to propose our artifact-centric approach which the basic idea is to leave ambiguity from the beginning, not remove ambiguity from the start in requirements, but leave it as long as possible to be able to analyze and understand the context at runtime, so that then we have more information to be able to resolve the ambiguity in the later steps. And we are presenting a 5-step approach, which is incremental. And it starts with capturing requirements, general requirement solicitation, and the artifact here is a specification, for example, early goal models. Then we go to the next step, which is identifying variability points. Like, for example, in the car example, we could have several different vehicles which would implement different variability. So this has to be identified, and then it's captured in models, for example, late goal models. Then we go over to the next step, which is the identification of certain contexts. And in this case, it's low-level context, like, for example, context attributes, which are then captured in context models, for example, ontologies. In the next step, we go then one level up, and we try to capture situations, now using the context attributes, but it's more high-level situations that would occur at runtime. And we capture it in situation models to have, for example, reasoning support. And in the last step, we look at the solution space, and then we have to design the variability, looking at the architecture, and then capturing it in architecture models, for example, component models. So this approach, we propose it to be iterative, so it can be iterated in several steps, and we can go back and forth from step 5 to step 4, and then back again as need is. So, for example, if at runtime we identify that a certain situation was not captured, then we can go back and try to understand, okay, what is the low-level context that we can use, which sensors can we use, and then go further up again to the next step and refine it iteratively. So I'm explaining each step now in detail, and I'm just presenting the general idea, then presenting the challenges that we see at the moment, and some ideas on how these challenges can be addressed. Step 1 is the general requirements capturing. And the idea is to have, it's just general requirement solicitation, the original requirement solicitation. And then for a self-adaptive system, we need it in a machine-readable notation, which is, for example, goal models. So these requirements are captured. And then the idea here is to leave ambiguity in requirements and not resolve all ambiguity from the beginning. So originally, in requirements engineering, ambiguity is not really always something that is good for the system, to implement the system. Now we are proposing that ambiguity is not really bad, because ambiguity can mean that we just don't have enough information at design time. But as we go along and we see more concrete details on the context and also situations at runtime, we can resolve the ambiguity in a better way if we go along in the later steps of our approach. But the challenge is, of course, how to consider which ambiguity we leave in requirements. So some ambiguity might need to be resolved, but other ambiguity might be really necessary for self-adaptive systems variability at runtime, because then the system might be able itself to resolve some ambiguity by determining what is existing at runtime and how can we exactly integrate and implement a certain goal. So ideas on how to resolve those challenges: to define different categories of ambiguity and their effect on adaptation capabilities of a self-adaptive system. So there might be several categories of ambiguity. Some are good, some are not good. Some can be resolved in one way, some might be resolved in a different way. And this has to be investigated and then kind of catalog proposed, kind of patterns, which then can be reused for self-adaptive systems. The second step is to identify the variability points. And our approach is an iterative process, and we can have 3 different cases. So there might be requirements where there's no variability at all, and the requirement is considered as solid with only one expected behavior. Then there might be requirements that are not ambiguous and its variability is completely identified already from the beginning. And then some requirements might be ambiguous requirements where a new variation of the requirement is produced for each interpretation and then is evaluated again. And then we can go back and see whether some of those variations are again ambiguous, and then we can refine them again further. So it's kind of a tree-based structure. Challenges, techniques and methods are required to provide, for example, runtime variability assurance. Like, how do we know that the runtime variability is implemented? And then unexpected variability and ambiguity management, when the system itself doesn't expect such variability to be there at runtime. How can the system handle it at runtime? And then alternatives to model the sub-specification of variability and adaptation requirements. So if we have this tree structure, how can we implement those sub-specifications of variability and define adaptation requirements? Ideas is to develop evaluation framework with techniques and metrics to assess the variability of requirements. And also develop runtime techniques to validate the variability of the requirements according to the states of the running system, and development of a runtime management infrastructure. So the infrastructure would support the sensing, analyzing, and acting upon unforeseen variability and ambiguity, which we didn't foresee at design time but is there at runtime. Next step is to identify context, and influence factors for variation points have first to be understood. And then the ambiguous parts of requirements can be refined further through context attributes. We have to identify those context attributes, and the context data can be either coming from the internal system itself or the external environment. Challenges to deal with step 3 is that we need techniques to support the identification of context attributes, and context attributes especially that are relevant to the variation points that we identified. And then the question is how to reduce invalid or not desired adaptation possibilities from an initial situation. So the system has an infinite possibility of context and context attributes. How can we reduce this to remove some invalid adaptation possibilities that are not desired? Some ideas is to model constraint of variables for particular values and evaluate them at runtime. So if we model the constraints, then we have some kind of restrictions already. And with the evaluation results, the system can reduce the adaptation possibilities of the model. So in the next step, we go one level further up, and we use this sensors and context attributes to identify certain situations. So these situations have to be defined. We have to analyze the context to identify the situations that are relevant to runtime events. So we have to exactly know the runtime events, and then identify the situations and define the traces between requirements and context situations. Challenges with step 4 is the information on the scenario might not be sensed by the system. So we might define certain scenario, but maybe it's not possible to exactly sense all the information through the sensor. So we have to really align the context attributes and the high-level context situations or scenarios. Then the next challenge is that situations or scenarios can be really subjective. So if one user uses a system, then for this user, maybe other situations are relevant than for a different user. So how can we make the situations more objective? And also the generation of all possible solutions or situations poses a risk to the system's performance. So if we have many different possibilities, then the system's performance might be affected by this, and we have to kind of restrict ourselves to only a certain state. We could implement runtime models to represent situations and required infrastructure to support the evolution of such representations. So then we keep track of the evolution over time. Also, strategies to guarantee the system's performance while generating diverse situations. So then the performance that I was talking about in the earlier slide is not affected. And the definition of influence factors mediated by, for example, scenarios to support more complex situations. So the more complex the systems become, the more complex the situations might become as well. And automatic derivation of possible situations only from those influence factors that we identify might kind of restrict the system already and the possibilities. And for step 5, we have to design the variation points in the solution space. So now we have to look at the solution space and provide a software solution that can satisfy the goals according to a given variability definition that we did in the steps earlier. And then also should be extendable when new goals emerge, because the approach is iterative. We might add new goals. So then the software solution should be extendable to new goals. And the realization must also especially support adaptation at runtime, because we aim for a self-adaptive system, then the adaptation at runtime should be supported. Challenges. So far we have knowledge about variability, but it's not fully reused at runtime. So this is one way to go in the future. And also DSPL approaches support this reuse so far, but the relation between design time and runtime variability is not well established yet. Ideas. It might be valuable to have different views on the variability data. For example, the design time view, which is suited for the requirements engineer, for the human, and then the runtime view, which is further suited for the software itself. It's for the system, the adaptation manager of the components that is then using this view to provide and support certain variability at runtime. And also knowledge that can be facilitated, that can facilitate automated decision-making at runtime. So because we aim for self-adaptive systems, and automated decision-making would allow for the self-adaptation. Conclusions. We sketched an artifact-centric approach for RE. Artifact-centric because we aim for self-adaptive systems which should document their knowledge, and the knowledge is documented in artifacts. And our proposal here is to leave ambiguity in artifacts to the later stages of the development to help refine the system adaptation over time as we have more information about the system and also the context and the environment at runtime. And for each of the 5 steps that we have presented, we described its purpose, challenges, and potential ideas on how to resolve these challenges. And with our approach, we envision a bridge between design time and runtime requirements engineering activities to manage ambiguities better, because we think ambiguities are very important to define the adaptation points in a self-adaptive system. Future work. It needs to be investigated. The challenges that we presented need to be investigated. Also, the corresponding evaluation of results would be very interesting to see. And then empirical research methods should be applied, quantitative and qualitative research methods, to further understand how the approach performs and in which cases it performs. So the applicability of all steps would be interesting to see in selected cases from industry. And I thank you for your attendance. And if you have any questions, please just drop me an email. I would be really curious to hear your feedback.